SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture number 7 of the course Robot Motion Planning. In the last class we have looked at the bug algorithm, in which we saw that the bug algorithm essentially is for a point robot, where the robot moves towards the goal, and in the process if it hits an obstacle it basically circumnavigates the obstacle, or it finds the M line and avoids the obstacle and then goes to the goal. So today we'll move on to the next step, that is we have a bug now, or a robot, which also has a range sensor. Okay, so from some distance it can figure out where is the obstacle and then take corrective action. After that we'll move on to the topic of configuration space. Now in robot motion planning this is something very basic, that the robot path is planned in the configuration space and not in the Cartesian space. So let's very quickly revise what we were doing in the last class, and then we'll move on to the next topic, which is configuration space. Okay, so today let's very quickly revise what we were doing in the last class and then move on to the next topic, which is configuration space. So in the last class we were looking at bug algorithm, okay, and we saw the bug 1 algorithm, which is shown on the left hand side, and we have a start point and we have a goal point. Now a couple of points to remember here. First is that the robot is a point robot, so it's a point which is moving in space. Number 2, it has some kind of sensor like a touch sensor. Okay, so it has to touch the obstacle to understand that okay, that's an obstacle. Okay. And how does the bug 1 work? So this is my bug 1 algorithm. So the bug 1 algorithm essentially starts by connecting the start point with a goal point, and then the bug follows the straight line because it has to move towards the goal. And once it touches the obstacle or hits the obstacle, what it does is it circumnavigates the obstacle, okay, and comes back to this point. Next, it has to find a leaf point. So this point is called the hit point, or we can call it Q hit 1. Okay. Now it has to find a leaf point. Now the leaf point is the point which is closest to the next obstacle or is nearest to the goal. Okay, so in case there is no obstacle, it can go to the goal straight, or if there is an obstacle, then go to the obstacle. So let's say it has circumnavigated and come back to the hit point. Now it will start this way again and go and find another point which is nearest to the next obstacle. Let's say it is this point. Okay, so what it will do now is it will try and go towards the goal again. Okay, and then it leaves from here and in a straight line towards the goal. It hits the next obstacle. Now it circumnavigates again, comes back to here, and then what it has to do is it has to find a point to leave. So this is my Q hit 2. So it has to find a point where it has to leave the obstacle and go towards the goal. So maybe it finds a point here. It goes like this, finds this point, and then goes there. Okay. Now something about the bug 1 is that it circumnavigates the obstacle. Okay. Now in bug 2 is a modification of bug 1, which appears to be faster, is that we have a start point and a goal point. So this is my bug 2. So what it does is it connects the start and the end point and the goal point by means of a straight line, which we call the M line here. And it follows the M line until it hits an obstacle. Then what it does, it goes round the obstacle till it finds the M line again. The moment it finds the M line, it follows the M line, goes round the obstacle like this, finds the M line and goes to the goal. Now it would appear that bug 2 algorithm is faster than bug 1 algorithm. But this depends on the shape of the obstacle. This is something we have seen in the last class, that in the case of a spiral, very often the bug 1 will succeed in finding a path and reaching the goal, whereas the bug 2 might fail. Okay, so it is very much dependent on the geometry of the obstacle. Now, two things that we talked about here. Number 1 is that the robot is a point robot. The next, it has a touch sensor. Okay, so that's how it finds out where is an obstacle. Now, suppose the robot now has an ultrasonic range sensor. That means it can find out how far it is from the obstacle. So let's say we have an obstacle here and we have the robot which is here now. It's a point robot, but it has an ultrasonic sensor. Okay. Now the range sensor has a finite range of detection that we know, and it can sweep 360 degrees. So if you can imagine that if I can mount a range sensor, so I have a motor here and I mount the range sensor. So this is my range sensor, and it can rotate about this axis by 360 degrees. Okay, so suppose if you can imagine this, Okay, this is my range sensor, and in this direction it is my 0 degrees here. Okay, theta is equal to 0 here, and it can sweep. As the motor rotates, what will happen? It will sweep and it will give me the distance. Okay, so first of all, there is a range sensor. It has a finite range, and the range sensor will prevent the robot from colliding with the obstacle. So in the previous case, it had to touch the obstacle. Here, it will not touch the obstacle because it knows the obstacle is there. Now, when the robot is standing at this point x, say xy, okay, is the coordinate of the robot at this point. Now, it also has a sweep angle. For example, whether it is seeing this side or it is seeing that side. So there is a theta, let's say this is equal to 5 degrees when it is seeing this side. So there are two variables here. When the robot is standing at this point, one is the distance it is from the obstacle. So this is my obstacle, which is given by x, and the angle at which the sensor is currently with respect to the 0. Okay. So using these two, what we do is we compute a distance function which gives us the exact information as to how far the obstacle is and it is in which direction compared to the 0 of the robot. Okay. So we define a distance function. Now, what is the objective of this distance function? The objective of the distance function is to find out the shape of an obstacle, right? We want to find the shape of an obstacle. So the distance function essentially consists of rho, which consists of x and theta. X is where the robot is in the workspace, and theta is the sweep angle. Okay, so x is my position, okay, and theta is my sweep angle of the range sensor. Say for example, if this is my 0 degrees, the next is going to be 5 degrees, 6 degrees. So now at any point here, and we are going to find out this distance function rho. So when we are going to get our rho will be a set of points, set of distances, which will actually tell me that at 0 there is nothing here. At 2 degrees, 3 degrees, 4 degrees, 5 degrees here, now there is an obstacle here. Okay, so this is the distance function which will give me this distance now. Similarly, for different thetas, okay, it is going to give me this distances, and these distances will indicate that there is an obstacle there. Okay, so now basically with respect to the position of the robot and the sweep angle, it knows exactly what is the position of the obstacles. Okay, so the objective of this is that the robot should be able to find out where it is with respect to the obstacles, okay, and then find a path. And to do that, we have to first find the rho distance function. Now, as we have seen that the objective is basically to find the profile or let's say the curves of the object. Okay, so in this particular case, the robot is at point x. It is sweeping from x is equal to from theta equal to 0, and wherever it gets the obstacle, you get a distance there. As we have seen, the way ultrasonic sensor works is basically if it hits the obstacle, the ray will come back and then it knows what is the distance of the object. Okay. Now what it has done is basically it has given us this distance functions, and we know that this is the profile of the object now, because I know the corresponding distances of every point on that object with respect to x. Okay, and because I know what is the sweep angle theta, I also know what is the orientation. Okay, so now I have completed my the range sensor has given me what? It has given me more information, that it is also telling me what is the shape of the object here. Okay, now the tangent bug algorithm basically relies on finding endpoints of finite constant segments of the curves. Okay, now why I need to find the endpoints? Because in between it doesn't matter, right? So if I have an obstacle like this, okay, this is my obstacle, and suppose I find that the range sensor is giving me this profile. This is the profile of the obstacle. It is enough for me to know where is the endpoints. Okay, I don't need to know what is in between. It may not be important for me, because I'm finding free path. So if I know this endpoint and I know this endpoint, then in between here and here is free path now. Okay, so I'm basically interested in finding the free path. That is why for all these curves we can find it is important to find the endpoints of these curves also. Okay, now we said the objective of this is not to go and hit an obstacle, but to keep a safe distance, and that is what the tangent bug does. So if I have an obstacle like this, okay, and this is my robot, it knows that the obstacle is here, okay, from the range sensor reading and the angle of sweep. So basically what it will do, it will not go and hit, because it knows the obstacle is there. It will go to some point and then it will turn right. It will become tangential to that point there, and that is why it is called a tangent bug. Okay. So it behaves like a bug algorithm, which is tangential to the surface at that point. So basically it will go like this, and then go off like that. Okay. So this is what we call the tangent bug algorithm, which works using the sensor data. We see that the sensor gives the information of the shape of the obstacle to the robot, right? So now we can see that we have a robot which is at a point, this red point, which we can call X. Now at the point X, it has got the information that the shape of the obstacle is like this. Okay, so now it has to decide whether it goes to point 1 or it goes to point 2. So we have point 1, we have point 2. There are many points in between, of course, but it doesn't matter. As we said that we are interested in the endpoints. So the endpoints are O1 and O2. So at the point X, the robot has to think, okay, and decide whether it will go towards 1 or 2, point 1 or point 2. So in that case, basically what it does, it minimizes this function. Okay. Now what is this function? D of X OI is the distance of the robot from the point X to the point 1 and the point 2. So there are two distances here. Okay, so there is one distance here, there is one distance here, and there is another distance there. Okay, that is one distance. The other one is D of OI to goal, Q goal. Okay, that is the other distance, which is the distance of the 2 points O1 and O2. That is one distance here, another distance there. Okay, so what it basically does is it minimizes the sum of D of Xi OI plus D of OI QI. That means it is going to basically measure this distance. This one plus this one is longer, or the other one is longer. This one plus this one is longer. So it will minimize that, which means it will go towards the point where this distance is less. So in this particular case, we can see that this distance is less, so the right side distance point is less, so it will go towards this side. It will go here. Okay, so that is how it decides which side to go. Now next we see that this depends very much on where the position of the goal is also. For example, in this figure on the left side, the goal is here, and this line is going straight through, because this distance was going straight through the goal now. Okay, so it is going to go from this point to here. Okay, the corner of the obstacle. Then it has to choose where it has to go. So whether it is going to go like this and like this, or it is going to go this side, that it has to choose. Now in the case on the right, you can see that the goal is right here. In the earlier case, the goal was there. Now the goal is here. So it doesn't have to go to the obstacle 1 at all. Okay, because very easily it can see that this is my straight line connecting the goal, and one end is here, the other end is here. So which distance will be less? This distance will be less. Okay, so it will go here, and then it will go in that direction. Okay, so it's not getting the obstacle 1 at all. So we can see that the path is very much dependent on geometry of the obstacles. Now the motion to goal is basically by executing the bug algorithm and by minimizing this distance, which is giving the distance between the position of the robot at X and the point where it is hitting the obstacle, that is OI, plus the distance between the corresponding point and the goal point. Okay, so it will always try to minimize that, and trying to minimize that, it will move. So you can see that at time is equal to 1 second, it is coming near. The range sensor is such that it doesn't see the obstacle. At point time is equal to 2, it is seeing the obstacle. Now it is deciding which side to go, whether this point or this point. And it decides it goes towards the right. Okay, so as it is going towards the right, it is seeing more of the obstacle, and it is going more and more towards the right using the bug algorithm till it comes here, and then it finally goes there. So what it was basically doing is it is minimizing this function, and this is something like it is thinking. The robot is thinking which side to go. Okay. Now transition from motion to goal is exactly in the same way. When it is going straight towards an obstacle here, basically it will try and transition, and then it will follow the bug algorithm. So when it is going towards the goal, what is happening in this case is that you can see that as it is going backwards, the distance is increasing actually. Okay, so here it will switch, it will transition from motion to goal, that is basically the bug algorithm, and try and go around the obstacle and then go towards the goal. Okay, because you can see in all the cases, it tries to go towards the goal, it doesn't go away from the goal. But in obstacles of this nature, what will happen is as the robot is pushed away, it is from the surface of the obstacle. Okay, it is following the obstacle, right? The profile of the obstacle. So the distance towards the goal is increasing here now. Okay, so now it is transitioning to the bug algorithm again, following the surface, and then it is going towards the goal. Now that is basically the boundary following behavior. So you can transition between this two behaviors and then try and go to the goal. So this is an example also where the robot was moving towards the obstacle. It finds the point M, goes towards M, but then after M, again this is concave. Okay, and this happens very often for concave obstacles. Now there is no other way, so it has to use the bug algorithm, or the tangent bug, follow the profile and then go like this and then come to the goal. Okay. Now, so far we talked about the range of the sensor. We talked about a point robot. Our robot is still a point robot. And we talked about the range of the sensor. Okay. Now the sensor has a range. For example, it can see maybe an ultrasonic sensor. It can see maybe 1 meter. It can see 2 meters. Okay. And it is circular like this. Okay, so this is my 0 and this is my scan angle. So if an obstacle comes in that circle of radius, whatever is the range of the sensor, then it can see, otherwise it cannot see. So if it has 0 range, basically it means that it cannot see. It's like a touch sensor. 0 range sensor is equivalent to a touch sensor. Okay, so it's equivalent. So in this particular case, you can see we have the start point here and we have a goal point here. Now we know which is the direction of the goal. So basically it always has to move towards the goal. So if you have a straight line there, then it starts off in that direction. It hits the first obstacle. Okay. Now once it hits the first obstacle, what it does is it minimizes the heuristic and goes towards the right. Whatever we have seen, it goes towards the right, is following this. From here, it again goes towards the goal and it comes here. Then again it goes around the obstacle, comes here, goes like this, goes here, goes like this, and goes. So this is almost similar to the bug 2 algorithm. Okay, because it is behaving like a touch sensor. Now, now suppose there is a finite range on this sensor. That means it doesn't have to go and touch the obstacle. It can decide whether to go left or right much earlier, the moment it sees the obstacle. So now you see what is happening to the path. So it started off from here and we are connecting with a straight line with the goal. It tries to go in a straight line, but the moment it has come here, the circular range of the sensor indicates that there is an obstacle there. Okay, so now it has to immediately decide whether to go left or to go right. So by checking the heuristic distance function, basically what it does is it goes right like this now. Okay, then from here it again goes towards the goal. So it has come here, again it sees an obstacle. Okay, so it has to decide whether to go here or to go here. So again it uses the distance formula. Which distance formula? This one. Okay, so it minimizes this distance function, which is the sum of the distance between the robot and the endpoint of the curve and the point on the end of the curve on the obstacle and the goal point. Okay, so by minimizing that, what it does is it finds the next point. So from here it has found this point. Then from here it starts going towards the goal again. Now it has hit the obstacle. Now it is finding these two. This is one point, this is another point. Okay. Now it is basically seeing the sum of the distance from here to here and from here to the goal. Okay, that is much less than the distance from here to here and that. Okay, so it will go towards the left now. So now it is going towards the left, following this curve, coming here, again the same thing, going here and then going to the goal. Okay. Now this is the case where it has a finite range sensor. Now suppose this has infinite range sensor. It can see really far. Okay. Then from here it starts off, this is a straight line, but from here itself it has infinite range, please remember. So it automatically knows what is where. So it can see this obstacle from there because it has very large range. Now it knows that this is my obstacle. So it doesn't go towards that obstacle at all. It gets the last point, the end of the curve. From here, it again sees, and it basically sees this one. Okay. So once it sees this one, it goes there. From here, it goes here, it goes there, and goes straight there. Okay. So this is basically showing a very large range sensor. And using the very large range sensor, it can find which points are hitting the obstacle. And then it is going from the start point to the first obstacle, second, third, and then it is not touching the fourth obstacle and going off straight to the goal. Okay. So if you compare these three paths, this is the path 1, which has 0 range sensor. You can look at the length of the path. This is the one that has a finite range sensor. It is a little better than the previous one. Okay, but the direction was more or less the same. But the third fellow, which had a very large infinite range sensor, the path was much shorter. So it simply avoided, it went to the corners of the obstacles and then simply went towards the goal. Okay. So this is basically to show that a lot of it depends on the range of the range sensor. So if your range sensor has very small range or large range, okay, so the path is going to depend on that now. Okay, now so far about the bug algorithm and the tangent bug and the heuristics that is used to decide whether the robot should go left or the robot should go right, okay, using a range sensor. Now let's come to the probably one of the most important topics in this course, that is configuration space. Okay. Now we have seen that robots occupy space and are of different sizes and shapes. Okay, that is something we have seen. For example, we can have a mobile robot which is circular like this, and it has two wheels. It has omega 1 velocity there and omega 2 velocity on the other side, and we have a caster wheel in front. Okay, so this is one robot, and we can assign an axis in this direction. Okay, so this is my x and that's my y, and this makes an angle of theta with the global axis. Let me draw the global axis here, x and y. Okay, so now we have seen that this robot is a circular robot, and we drive it by omega 1 and omega 2, and this is a differential drive robot. Okay, so it goes forward, it can turn simply by changing the ratio of omega 1 by omega 2. Okay, now we have another kind of robot which is let's say a car-like robot. So we have a wheel which is connected here, and we have a steering wheel here. Okay, let's say we have a steering wheel. Now let me just have one steering wheel here. Like an auto or a tempo, you must have seen that. There's a steering wheel here. So this is omega, and that has the steering angle which is phi. Now this also has the point xy which is there. This is my axis. Okay, this is my y-axis, and there is a phi there which is the turning angle. Now this robot also, so this is my turning angle phi. This robot also makes an angle of theta with respect to the x-axis of the global. Okay, so this is another kind of robot where the input is omega and phi, okay, to make it go. Now you can also have a serial arm where we have a serial arm robot like this. Okay, so we have one, you can imagine this is multiple degrees of freedom, 1, 2, 3 DOF arm. Now these arms are going to have physical lengths, they'll have physical dimensions. So that's my arm. Okay, so now what we have seen that these robots, mobile robots and serial arms, you can even talk about a flying robot, quadcopter. These robots occupy space in the real world. Okay, they are not points. Basically, robots are not, real robots are not points. Okay, as we have done in the bug algorithm case. So there are different kinds of robots, and they occupy space and are of different shapes in the real world. Okay, so now what we need to do is, when we are doing the path planning, in the case of the bug algorithm, we had a mobile robot which had a sensor in front. Now, what is the objective of this path planning? The objective of the path planning is that the robot should not hit obstacles. Okay, that is English language. Robot should not hit obstacles. What is the meaning of this? It basically means, in terms of geometry, that no point of the robot should be inside an obstacle. Okay, so for example, I have a mobile robot like this. This is a mobile robot, differential drive with a caster in front, and I have an obstacle. That's my obstacle. Okay. So this fellow has a point xy and it has a radius r. Okay, so when we are saying the robot should not hit the obstacle, it basically means that no point inside the robot, okay, geometrical, these are points inside the robot, right? No point inside the robot should be inside the obstacle. So if this is my obstacle, the robot should not go, and no point of the robot should encroach upon the obstacle and go inside the obstacle. This is what it means. Okay, so this is my, so these points should not go inside the obstacle. Geometrically, this is the meaning of do not hit the obstacle. So no point of the robot should be inside the obstacle, okay, inside the obstacle boundary. Okay, so the question that comes up here is, if you're talking about a point, that's not very difficult. Like in the case of bug algorithm, we had an obstacle and there's a point. You can check if the point is inside that boundary or not. Okay, geometrically we can do that. But in the case of a real robot of different shapes, for example, here we are having a robot which is circular. Again, it's easy to understand that there are different points and this point should not be inside the obstacle here. What about in the case of a serial arm? There's an obstacle here. Okay. Now, any point on the link should not be inside this obstacle. That is not very easy to visualize. Okay. In the case of mobile robot, it's a little easier. In the case of serial robot, it's more difficult. Okay. So, what is or how much information is required to completely specify every point of the robot? Because we are saying that no point of the robot should be inside the obstacle. Okay. So, how much information or what information is required to completely specify every point of the robot? If we can do that, then we can ensure that no point is inside the obstacle. Okay. Because we are ultimately going to check geometrically, right? So we'll see if there is any point of the robot inside the obstacle. And how do we do that? We check it geometrically. Okay. So let us take the example of a circular robot. We'll come to arm manipulators a little bit later because they are a little bit more tricky. Now, a circular robot of radius r can only translate but not rotate. Let's make this assumption here. So we have a circular robot. This is my circular robot. These are two wheels of the robot. Okay. There is a caster wheel and it has radius r. Okay. Now, we are saying that this robot can translate, okay, and it cannot rotate. This is the CGXY. Okay. Now, if we know the center point XY and the radius, then we know all points of the robot because we know the radius of the robot. So, if I have the center point of the robot here, this is my XY, okay, and I know the radius of the robot, which is R, then if I draw a circle here, then I know all the points inside. Okay. So, what is enough here? So, what is enough to know is only XY. So, if I know the center of this robot, because it's a circle, okay. So, if I know the radius of the circle, then I know all the points inside this robot, okay. So, if I know the center point, so if I know the center point XY and the radius, then we know all the points of the robot, right. So, here again I am showing XY is here. If I simply say XY is here or here or here or here or here, then I know where the robot is also because I know the radius. So, the information that is required here is the XY of the robot is required, and this XY represents the configuration of the robot. Okay. So, here we are using a new term, that is the configuration of the robot. So, the information required to specify all points of the robot is called that is basically the configuration of the robot, and a collection of the configurations makes up the configuration space. Okay. So, this is the information to specify all points of the robot. Okay. So, what is this information? It is XY. Okay. And so, what we say is that two parameters x and y are enough to specify all the points of the robot. Why? Because r is known. Okay. So, the radius of the robot is known. That means if I tell you xy, now you know where the other points of the robot are. Now, these two configurations, these two parameters make up the configuration of the robot. Now, configuration space in short is called C space. So, it is the space of all the configurations of the robot. Okay, now I hope you can make the connection that all the XYs of the robot, okay, make up the configuration space. A collection of all the XYs of the robot make up the configuration of the robot. Okay. Now, the configuration is just a point in C space. Okay. That basically means it's a point, right? Because the robot has shrunk to a point now. As the example I gave here, I was talking only about XY, that is X1, Y1, X2, Y2. These are just XYs, okay, collection of the configuration of the robots. Okay. So, the configuration is just a point in C space and the robot has shrunk to a point. Okay. So, please note that we have Cartesian space and we have C space. Now, let us say that this is a work area of a mobile robot. Okay. We have a mobile robot here, okay, which has radius r and its center is xy. Okay. This is my workspace. Now, the configuration of the space is a collection of all the configurations of the robot. Okay. all the possible configurations. Now, obviously, this robot cannot go out of this boundary. It cannot go like that. Okay, so this point is out of the configuration space. It cannot go out. So what is the maximum this robot can go? The maximum the robot can go is on the boundary. Okay, remember it can translate only like this, like this. Okay, so it can go and sit on the boundary like that. That's the maximum. Inside is okay. It can go anywhere. So when it goes and sits on the boundary, this is my xy, xy, xy. So now if I'm saying that the robot has shrunk to a point, I'm only interested in the xy of the robot, then this space has shrunk to this distance now. I hope you remember, you understand that. Okay, so what has happened is the robot has become a point, and the workspace, the boundary, has shrunk by how much? By r. So it has come down by r. That means all the points here are actually possible. So now here I'm converting this into configuration space, and this is my configuration space. So the inside fellow is now my configuration space. Okay, this is smaller. Let me draw it here. Okay, it doesn't look smaller, just longer and smaller here. Now let's say that now. Okay, now what has happened is this has become my configuration space now. So this is all the points where the robot can go. Now the robot has become a point. So robot has become a point because it only has xy, it doesn't have anything else, and the boundary has shrunk by r. Okay, so this is my Euclidean space. It is also called Cartesian space, which you are familiar with. If I say this is my xy, this is my xy directions, okay, then this is my Cartesian space, the one shown on the left. The one on the right is my C space now. Now the C space and the Cartesian space, they look same. Why? Because we are talking of xy only. Okay, but they are not actually the same spaces. As we go along, we'll see how. Okay, so please, I'll just repeat again whatever I have done, because this is very, very important. We are saying that the robot should not hit any obstacle. Okay, geometrically, what does this mean? This means that no point on the robot should be inside the obstacle. This is what it means. Okay, and geometrically we can check that. Now to do that, we need to know how much information is required to completely specify every point of the robot. Okay, now and in order to do that, what we see is that if you know where is the center of the robot xy and you know the radius, then if you know where is xy, then you know where the other points of the robot is. Like if I give you xy here, x dash, y dash, the robot is there, then I immediately know where are the other points. The other points are all here. Okay, so xy is the information required to find out or to specify all the other points of the robot, and this xy is called the configuration of the robot. Okay, it is like saying the robot has shrunk to this point, which is xy now. Okay. Now these two parameters make up the configuration space, which we call the C space. Now if you have a workspace like this as shown on the left side, okay, and we have the robot, then what are the possible configurations that the robot can go to without going out of the boundary? Okay, at most it can go and sit on the wall. Inside is fine, there's no problem. At most it can go and sit on the wall. Now if it goes and sits on the wall or touches the wall, then this is my r distance, the center of the robot. That means the xy can only go till here. It cannot go into that space there. Okay, so it cannot go inside in this space. The xy cannot go into that space. Okay, that is very clear from here. Okay, why? Because the center cannot go inside there. That means no point, the robot, it will not be possible for the robot to go here and sit like this. In that case, it has gone through the side, which means that the boundary has shrunk by r, okay, and the robot has become a point. Okay, and the collection of all those points is basically what make up the configuration space. So this inside boundary is what is drawn here. Okay, so the robot has become a point. Now all these points inside here are possible positions for the robot to go. Okay, there's no problem. It can go anywhere. It cannot go outside the boundary only. Okay, so this collection of points is basically called the configuration space. Now please note that the Cartesian space, which is shown on the left, or Euclidean space, is different from C space. They look the same, okay, because this also looks like there is x here and y there. So they look same, but they are not. Okay, so the C space looks like Cartesian space or Euclidean space. Now the degree of freedom, okay, so these are terms, so let's go slowly. The degree of freedom of the system is the dimension of the configuration space. Okay, so mobile point robot, the degree of freedom is 2 because there is only x and y. Okay? And that is why we said that it is not rotating, it is only translating. Okay, now the robot shrinks by r, the obstacle and boundaries expand by r. Okay, so let's look at this case. So in this case, if we have a workspace like this, okay, in the previous case I did not have an obstacle, I only had the robot. The robot shrinks by r, the radius. Okay, so it becomes a point, and the outside boundary also becomes smaller. So it will become smaller like this now because it has shrunk by r, right? Because the center of the robot cannot go anywhere inside there. Now what about the obstacle? Well, the same logic applies. The robot can go and sit at most on these points on the obstacle, on the boundary of the obstacle, right? It can't go inside the obstacle because we said that hitting an obstacle basically means points of the robot have gone inside the obstacle boundary. So now we see that again the same logic applies. If this is the center of the robot, okay, the CG, the central point, then there will be a straight line like this, curve like this, straight curve like this, right? So what has happened is that this is my Cartesian space and I'm converting it. First of all, it has become smaller. Okay, so this inner fellow has become here. So this is my inner fellow. So the inner one is here now, which has become smaller by r. Okay, and what has happened to the obstacle? The obstacle has become larger. Okay, so the obstacle has become larger. Okay, so here we can see that what is happening to the obstacle, it is becoming larger. Okay, and it has gone out this side. Okay, so what we are seeing is that the obstacle space has become larger now. That's my obstacle space. So the obstacle space has now become bigger. Okay. Now this is interesting. Why? If you look here, okay, now it was not clear if the robot could go through that space or not. But here it is very clear that there is no space here. Okay, the obstacle has taken away all the space. That means the robot cannot go from the bottom now. So the robot has become a point. It can go at all points here. Okay, it cannot go outside the boundary, of course, and it cannot go inside the obstacle. Now it is very clear, okay, that these are points where the robot can go, and these are points where the robot cannot go. Okay, so we have reduced the robot to a point. We have shrunk the workspace, the boundaries, and we have increased the size of the obstacle. By how much? By r. So the obstacle has become larger by how much? By r again. It is like the obstacle has expanded and the robot has shrunk. Okay, now this is my C space. Okay, and this is my Cartesian space. They look like they are same, but they are different spaces. Okay, in the case of a serial arm, we'll see that the spaces even don't look same. They look very different. Okay, when you look at it. Now, this will also give a clearer idea of what is the use of this. Okay, the use of this is that we can very easily find a path from one point to another point. Why? Because it's a point which is moving in space, and as long as the point is not inside the C space of the obstacle, then the path is fine, right? So when we are trying to find a path, for example, in this case, let's look at case 1, case 2, and case 3. 3 cases. There is an obstacle here, so these are the obstacles. The workspace is given. In the first case, the robot is a point robot. I have to find a path from the start, let's say start to goal, start to go, start to goal. Okay, so now in the first case, the robot is a point robot. Okay, we have the obstacle, so there's no point, there's no problem at all. This is our free space, so the robot this point can go anywhere as long as it doesn't go inside the obstacle. So we can very easily find that there is a path like this, okay, or there is a path like this. There are multiple paths actually, which can take the robot from the start point to the goal point, okay, which is very clear. So we are converting this into C space because it was a point robot. It still remains the same. There's no change, and we can find a path like this, for example. Okay, and it's also clear that it can go from the bottom like this to this point. What about example 2? In example 2, the robot is not a point robot. It is having a radius r. Okay, so now if I want to find out whether the robot can go like this, okay, just by visually looking at it, it's not very easy actually to say. Okay, plus this is geometry, right? The robot doesn't have any eyes. You're writing a computer program, which is the, when we say path planning algorithm. So algorithm is a program. So the program has to find out if the robot can go like this or not. We have eyes so we can see, but even then it's difficult, right? But now if you see, we are converting this into C space. The robot is shrinking and becoming a point, and the obstacle is increasing. The boundary of the obstacle has increased, okay, and it is becoming this shape now. Now it is very clear that there is a path, but the path is like this. There is no path on this side. It cannot go through the obstacle. Okay, so we do our path planning in the C space. We don't do it in Cartesian space. Now let's look at the third case. We have a robot which has a larger radius. This R is, let's call it R dashed. This is my case 3. So in case 3, the robot is a little larger. Now can you say, can the robot go through here? Can it go through here? Here probably it cannot go through. Simply by looking we can say. What about the top? It's difficult to say. But for a program which doesn't have eyes, okay, what we basically do is we convert the robot to a point. That means shrink it by R, and expand the shape of the obstacle. And if we expand the shape of the obstacle, what we see is that it covers the boundary here. It is also covering the boundary here, which basically means there is no path which will take it from here to there. There is no path, which was actually difficult to say just by looking at this figure. Okay, this was difficult to say. Okay, but here it is very, very clear. It is extremely clear that there is no path, because the two sides, the start and the goal, are disjointed. Okay, there is no connection between this side and this side. Okay, so how can it go? Okay, so this gives us an idea of how to go from the Cartesian space to the C space. And now if you're wondering about the shape of the obstacle, like in the previous case also when I drew, what you're seeing is that what is happening here on this side is that there is a curve which is coming. When there is a sharp corner, okay, what happens? The curve comes. Okay, now how does that happen? Let's just look at a little bit more. Now let's say that we have a robot. This is my workspace on the left side, and we have a robot which is having, this is my robot which has radius R, okay, radius of R, and this is my obstacle. Okay, so this is my obstacle. Now I want to draw the C space, this workspace, or we can call this the Cartesian space. So I want to make the C space now. So what would happen is I'm going to reduce this, I'm going to shrink it. Okay, let me say I'm shrinking it now. Okay, I'm shrinking this by R, so this has become smaller. Plus, I'm going to see all the possible configurations where the robot can go without going inside the obstacle. Now, how do we do that? If you can imagine, let's look at the obstacle here now. Now, if you can imagine, the robot is a circular ball, and you are moving this circle along the boundary of the obstacle. Okay, so this point is, you are shifting the radius, you're moving the CG like this. Okay, so the robot has come here. Okay. In this case, the robot is here. So I'm simply sliding the robot. Okay, so the robot is being slid. Now it is being it is sliding, and this is the locus of the center points. Okay, so this side has increased there. What is happening at the corner? Please look at the corner very carefully. The robot is here, so it is making point contact here between that vertex and the ball on the circle. Now, on this point, the robot can actually, it's like saying this circle can actually go like this, because it's making a point contact. So this is if you can imagine that this is the point, this is the point, and this is a circle at that point. So the contact it is making is a point contact there. So this is the circle making that point. Now when the circle is on this side also, okay, it is the same point. It is like saying the circle has rotated like this. The CG has moved like this. That's where this arc comes from. So you can see that there is an arc here, this arc. Okay. Similarly, in the case wherever there is a sharp corner here, so we can have the robot sitting here. It is making a contact at that point. Okay. And when it is sitting a little bit on this side, on the right side, that is here, that contact point is still the same. Okay. So in the process, what happens is it is like the robot has rotated a little bit. So an arc comes in there. So you see the shape of the obstacle of the C-space obstacle is that there are curves wherever there are sharp corners. So you can see that there is a sharp corner here, there are curves on this side. Okay, so now we understand how to make expand the shape of the obstacle. Exactly the same thing I did here. When you look here, there is a sharp corner. So what happens here, you can go and sit on that point actually, right? On this point or here, the CG, the contact point is still the same, but the CGs are different, right? Because it's an arc there. Okay. So in both positions, position 1 and position 2, the two extreme cases, the contact point is still the same point. Okay. It's like the circle is rotating about that point. Okay. Now this is how we make the C-space obstacle. Okay. So what has happened is the workspace has become smaller by a small amount, by amount r, and the obstacle has expanded. Okay, how it has expanded, let me just draw the shape. So there'll be a curve here, there'll be a curve here, and there'll be a curve there. It will become like this. It's going like this. Okay, so that's how we have come from here to there. Okay, now if I were to draw the workspace here, and let me just complete the workspace. So this is my workspace. Okay, so this is my workspace. So workspace is this one now. Okay, so now the robot has become a point, so it can go anywhere inside here. So if I want to go from one point to another point, say I want to go from the left side is coming out of the boundary area as we are seeing here. So this has come out. So the left side boundary is hitting this. So it will go like that. So it cannot go there. Okay. So now to find a path from start point to goal point, it can go like this. It cannot go on the bottom side. Okay, because there is an the obstacle is going out of the boundary now, so there is no way. Okay. So this gives you an idea of how to convert the robot to a point robot, and then how to go from the Cartesian space to the configuration space. Now let's see a little further and see that we have for other kind of shapes. Okay, example of real world configuration space. So we have an obstacle and we have a mobile robot, which is a circular robot. Now the obstacle is marked in black, and we want to convert this into the configuration space. So what do? I shrink my robot by r. It becomes a point, and I increase this obstacles by the corresponding amount, that is by r. So here it will become a curve. Wherever there are sharp corners, there will be a curve. Okay. Similarly here, so this will I can simply, wherever it's possible for the robot to go and sit. Okay, so I'll take the locus of the CG, the center of the robot, and I'm going to complete it. Okay, so it will be like this, like this. Here it will be curved. It will go like this, curved, again like this, curved, again straight, curved, down, curved, and back here. Okay, so now what has happened is this outer space has come down by some amount, by r, not some amount, by r, and the corresponding obstacle has expanded. Okay, let's look at a little bit more here. So the yellow one is showing where the robot is going and sitting. So it is something like this. My robot now. That's the CG. Okay, so you can see very clearly that in the previous case, there appeared to be gaps here. There appeared to be gaps there. Okay, but and gap here. So it was not very clear the robot could go that side. But the moment we have come to configuration space, what has happened is, you see there is no space here, no space here. Similarly, there is no space there. Okay. So now if I want to go from one point to another point, I have a start point here. Let's say this is my start and this is my goal. Okay. Then the only possibility is that I have to go from this side. I cannot go from any other side. Okay, because it is very, very clear now. So what it basically did is, and what you can imagine and guess by now, is that before starting our planning algorithms, we can come to the configuration space and then convert the robot to a point, then plan the path for a point robot. Okay, path for point robot. Okay, so we're finding the path for a point robot. And the other thing that also becomes very clear from here is that the configuration space looks like the Cartesian space, but it is not the Cartesian space. Okay. Now, so what you can guess from here is that the whole of path planning algorithm actually has to do with free space and obstacle space. Okay, so that you would have guessed by now. So if you want to find your path, you basically divide the C space into free space and obstacle space. Okay, so this is my free space and this is my obstacle space. This is my obstacle. Okay, so basically the path has to go from start point to goal point without entering into the obstacle space. Okay, that means it has to move only in the free space. And that's not very difficult because geometrically you are moving a point. So if you know what is the coordinates of this points, or you know the vertices of the point, you know the coordinates here, right? So you can just check that if the point should not go inside anywhere there. That is the meaning of the robot going inside an obstacle. Okay. So the paths are basically planned in Cartesian space, and this is how we come to the Cartesian space. So today we will stop here and then proceed. Now what I would suggest is that please draw a few sample spaces, okay, Cartesian spaces and C spaces, and then for a mobile robot, please understand how we move from the Cartesian space to the C space, and also understand that why we are doing this. It's very important to understand that path planning will be basically done for a point robot. Otherwise, if you're trying to plan for a circular robot, which is moving in different directions, you can imagine that. And you can, of course, imagine in the case of the arm robot, a serial arm. Now, where the serial arm is going in which direction, whether it's interfering with an obstacle, that's extremely difficult to find out. Okay, but if you convert it into a point, then it's pretty easy. Okay, you know this is obstacle space, that's free space. Plan your path in free space, and that will ensure that you're never hitting the obstacle. Okay, so we'll stop here today, and we will continue in the next class. So thank you.